Hi, I'm Vicki Meyers and this is my presentation for Math 5170. I am a grad student, so I had to choose two questions to present. The first question I chose was question C. It states, a student asks, is there a relationship between the secant line and the secant function in trigonometry? And how do you respond? Well, my response to this would be, yes, we can establish a relationship between the secant line and the secant function. To do this, what I wanted to do was review some definitions and terminology with the student. So assuming this is a high school student, I used our high school geometry textbook, Geometry Common Core, for these definitions. So the way that this textbook defines secant line, it defines it as a line that intersects a circle at 2 points. In this diagram, you can see we have a circle, and its center is point A. And lying on the circle we have points B and C. So the line that intersects points C and B in the circle would create a secant line. The next definition taken from this textbook is that of a tangent line. And the book defines it as a line in the plane of a circle that intersects the circle at exactly 1 point. So again, you can see we have a circle centered at point A. And we have point B that lies on the circle, and since this line intersects that circle at exactly only 1 point, that being point B, this is a tangent line. In this explanation, my tie to the secant function is going to be through the secant ratio. So next I would review right triangle trigonometry with the student. Here we have a right triangle ABC with the right angle at angle B. And in this right triangle, we define or put angle theta, located here at this acute angle. And opposite of angle theta, we labeled the side opposite. Next to angle theta, we labeled the side adjacent. And the hypotenuse is opposite of the right angle. We have the 6 trig functions: sine, cosine, tangent, cosecant, secant, and cotangent. Now, since this student did ask about the relationship between the secant line and the secant function, I am assuming they are familiar with these definitions, but just to make sure they were understanding, I might run through and review these definitions with them. Sine theta is equal to opposite over hypotenuse, which means that the sine of angle theta is the length of the side opposite of theta over the length of the hypotenuse. Cosine theta is adjacent over hypotenuse. Tangent theta is opposite over adjacent. Cosecant theta is hypotenuse over opposite. Secant theta is hypotenuse over adjacent. And cotangent theta is adjacent over opposite. These definitions were taken from my Algebra 2 high school textbook, Algebra 2 Common Core. Now that we have reviewed some definitions, let's take a look at a diagram. To create my diagram, I went to geogebra.org and was able to use this to create a diagram. So let me log into this app. And we'll take a look at what we have here. Okay, so what I did is I started with point A at the origin on the X and Y axis, and I created a circle that had a radius of 1 unit, making this the unit circle, which is what we're going to use to make our connection between the two secants. I put point B out here at the intersection of my circle and my x-axis. I put a point C on the circle, and I put that in quadrant 1 for convenience. And what happens, or I shouldn't say what happens, I'm getting ahead of myself. I now have a line going through points A and C. And because this line intersects the circle at 2 points, this is a secant line. I'll place point D on the x-axis, and I can drop a line segment perpendicular to the x-axis from point C to point D. This creates a right triangle, ADC, and we'll put angle theta in here between our secant line and our x-axis. Because we have a right triangle and angle theta located here, we can identify this side as being the hypotenuse. We can identify the side opposite of theta as opposite, and we can identify the side next to theta as adjacent. From our previously defined trig functions, I know that sine theta is opposite over hypotenuse, and I know that cosine theta is adjacent over hypotenuse. If I come back out here to point B and give its coordinates as 1, 0, then I know that the radius of this circle is AB, and it's equal to 1 unit. I also know that AC, segment AC, is a radius to this circle, and since the radius is 1 unit, I can say that the length of AC, or segment AC, is the radius, and it's equal to 1. So our hypotenuse measures 1. What I can do now is come up to point C and give that an arbitrary point xy. And if that is point xy, then I could say that segment AD is x units long, and I could say that segment DC is y units long. And what I can do is take these values and plug them into my sine function. So since sine theta is opposite over hypotenuse, and opposite of angle theta would be my y, I can write that as y over 1. Remember, my hypotenuse is 1. Or essentially I can say that sine theta is equal to y. And so I'll highlight this in blue. This segment, the length of this segment, would actually represent the sine of theta. I can do this with cosine. Cosine theta is adjacent over hypotenuse, and my side adjacent, we said, could be labeled as x. And so cosine theta is x adjacent over the hypotenuse, which is 1, or basically cosine theta equals x. And so you can see highlighted here in pink that this side of the right triangle represents, that length represents the cosine of theta. Next, I'll draw a line tangent to the circle at point B. Drawing this line tangent to the circle at point B creates a new right triangle AB. Well, let's give that a label up there, ABE. If I label point E as the intersection of my tangent and secant lines, I now have triangle ABE, which I will highlight in red. Okay. So here's triangle ABE, and it is a right triangle, and I have angle theta, and now my adjacent side becomes segment AB, and that adjacent side has a measurement of 1 unit. My hypotenuse is segment AE. Even though it's kind of outside of my unit circle, I can still use the unit circle for measurements. So the length of the adjacent side, we just said, was 1 unit. So AB is 1 unit. And if we remember our definitions for the secant function, we know that secant is hypotenuse over adjacent. And I have the side adjacent here now highlighted in green, and that is 1 unit. My hypotenuse is segment AE. And so I can say that my secant of theta is hypotenuse over 1, since my adjacent side was 1 unit long. Or basically I can say that my secant theta, secant of angle theta, is the length of the hypotenuse, which is segment AE, which I'll make a little bit darker red here. Notice that segment AE, which now represents the secant of angle theta, lies on my secant line. So in doing this, we were able to establish some type of a relationship between the secant line and the secant in trigonometry. Now, following up with the student, some ways I might get the student to expand on their thinking. I might ask them the question, is there a relationship between a tangent line and the tangent function in trigonometry? And basically, they could use the unit circle much like we did with the 2 different sized right triangles and establish that relationship. We'll take a look at that in a moment. Another question that I could follow up with the students on is there a way we can use the unit circle to show cotangent and cosecant ratios? This one is not quite as obvious as the tangent one will be, but there is a way to do it. One of the resources I used, besides the 2 high school textbooks, was a website called Visual Trigonometry. And this will help answer those follow-up questions that I just asked the student. So you can see that right here we have how I started. We started with a unit circle, and we drew a secant line through the unit circle, and we had theta. Now what this website does is they also place a cotheta, the other acute angle, in the first quadrant. As we talked about, this green line represented the sine of the function, and they dropped a tangent line to the circle, and they created the larger triangle, although still utilizing the unit circle. And well, I didn't use this too much, but as we come down here, you can see that the 3 functions of theta measuring sine, tangent, so that's where the students could see where the relationship between tangent of tangent line and tangent in trigonometry, and then the secant line was the hypotenuse of the larger right triangle. Again, making the relationship with cosecant and possibly cotangent, you'd have to use the cotheta angles, which may be a little advanced for high school students, but for, you know, expanding on their thinking, they could do this. But the tangent of cotheta would also be the cotangent of theta, and the secant of cotheta would be the cosecant of theta. So that would allow them to make that relationship between tangent, cotangent, and cosecant. Another interesting piece of information that this website had was its ties to the Pythagorean theorem and the Pythagorean identities for trig. So there would be another way that they could tie cosecant theta and cotangent theta together. The Common Core standards that could be identified for use in this type of question and this type of explanation was geometry, similarity in right triangles, or G for geometry, S, R, and T. Number 6, to understand that by similarity, side ratios in right triangles are properties of the angles in the triangle, leading to definitions of trigonometric ratios for acute angles. G, SRT 8, use trigonometric ratios in the Pythagorean theorem to solve right triangles, although we really didn't do any solving, but we used the trig ratios there. And FTF 2, that would be under functions and trig functions number 2, to explain how the unit circle in the coordinate plane enables the extension of trigonometric functions to all real numbers. Again, we didn't really do that, but we did use the unit circle, so it did have some relationship to these standards. Now, the standards for mathematical practice that I identified in this problem would be, first, to make sense of problems and persevere in solving them. Basically, you want the student to understand the problem and find a way to attack the problem and work until it's done. And that's kind of what we did with the unit circle. We went outside of the triangle that we're used to working with the unit circle, but we knew that we had to use the unit circle to get there. The second would be to use appropriate tools strategically, and I guess in this mathematical practice I'm counting the unit circle as a tool. The third would be to look for and make use of structure. I want the student to be able to take what they know about the unit circle and sine and cosine and expand on that. And the fourth would be to construct viable arguments, and this is just about being able to talk about math and using the mathematical language.